Hey guys, this is the first video for chapter 2 where we talk about atoms, ions, and isotopes. So we talked in class about the history of the atom. Remember, it started with Democritus, that there was something out there that was indivisible. And it was just an idea at the time. And this is really kind of a cool time for thinkers, right? I mean, these guys sat around in their robes all day and got paid to think. But that was the idea, that there's something that if you took anything and you broke it down to, you divided it in half over and over again, you'd eventually reach something that was indivisible. And that's what was Atmos, indivisible. And then Dalton came along and said, well, everything is composed of atoms, individual, unique atoms. That's that solid blue sphere there, representing Dalton's model. And because of how atoms react, a lot of Dalton's postulates remained true. Things like the law of multiple proportions and the law of constant composition. But then we discovered that there were things smaller than an atom, electrons. Remember, Thomson was credited with the discovery of electrons. And so he came up with the plum pudding model. Okay, that's what you see there on the orange and green. The plum pudding model was just electrons stuck in a positively charged goop. Because we don't spontaneously explode into a billion pieces, right? So there had to be something keeping those negative charges together and kind of balancing out that repulsion. And so that's what he said, was that this just positively charged goop. And then Rutherford came in and he discovered the nucleus with that gold foil experiment. Remember that crazy, it was a crazy thing to discover at the time. Remember, he said that it was like shooting an artillery shell at a piece of tissue paper and it coming back and hitting you. And so we got the nuclear model, and that's kind of, I guess, what a lot of people think the atom still looks like as far as our understanding. And I want you to know right now, we'll get to it in chapter 6, but that's not the end of the story. There's a couple more that we'll talk about even this semester. But that's where we stop now, because we can kind of talk about some of the things that atoms do. Now, taking a look at the periodic table, there's a number of things that we can discuss just marking on this periodic table. One are the locations of metals and nonmetals. Okay, so looking here, if we draw that zigzag line that you're used to seeing, right, we get the difference between metals, nonmetals, and metalloids. So most of the things touching this zigzag line here. So we got boron, silicon, arsenic, et cetera, except for polonium and aluminum. Those are all metalloids. Everything to the right up here are non-metals. Up there. That means everything, all of this, those are all metals. Okay. Now there's a couple of groups that are important, which we'll talk about again at the end. But we have the alkali metals, the alkaline earth metals, way over here on the right, the chalcogens, halogens, and noble gases, which we'll talk about again at the end. What else? We've got, if we look at the periodic table, we'll just kind of write out something here. Carbon. We've got a number, and we've got a number down here. Now, this is the atomic number, and that is the number of protons in the nucleus of that element. Remember, protons decide what the element is. There is never a carbon with 5 protons, and there's never a carbon with 7 protons. If it has 6 protons, it is a carbon. Now, down here, we have the atomic mass. Now, the atomic mass is based mainly on the protons and neutrons. Because electrons are so small, we normally neglect or just kind of don't pay attention to their mass. But that's kind of odd that we have things like chlorine, 35.45. How do you get 35.45 if a proton weighs 1 AMU and a neutron weighs 1 AMU? There's some decimal places out here. But if they're basically whole numbers, how do we get 35.5? Well, it's because of something called an isotope. Okay, An isotope is anything that has any element that has a different number of neutrons. Here we've got two carbon nuclei, okay, right here and here. And the carbon nuclei all have the same number of protons. That's in red. You can see they both have 6 protons. But the difference here is the number of neutrons. This guy has 6 neutrons, and this guy has 8. Now, without the picture of the nucleus, how do you figure that out? Well, this number is the mass number, okay? And this is the number of protons plus the number of neutrons. So if you're given the mass number and the element, you can easily figure out how many neutrons are there. Now, what does this have to do with the mass? Well, we have a little formula for figuring out atomic masses. It's this one right here. We have the mass is equal to the abundance multiplied by the mass of that isotope. So here we have an example of nitrogen. Okay, here we have an example of nitrogen. 1, 2, 3, 4, 5, 6, 7. It looks like there's one extra, but these are the numbers for nitrogen. You can see that we've got 2 different isotopes and 2 different abundances. So what we do is we plug it into that formula, and we can get our atomic mass. So here we have the mass, the exact weight of this isotope multiplied by its percent abundance, plus the exact weight for this isotope multiplied by its natural abundance. Again, these are natural abundances in their decimal form, so don't multiply by 99.63 or something crazy like that. Pretty easy equation, not too bad. Now the big part, I guess the main point of the first section of chapter 2 has to do with ions. Now in order to understand what ions form, you also have to understand something called valence electrons. Valence electrons. Okay. Valence electrons are the electrons that an atom uses to bond with. Okay, it's the electrons that the atom uses to do stuff. And thankfully, the number of valence electrons is equal to its group number. Okay, so if we go over here, you'll see this as A1, A2, way over here, A3, A4, A5, A6, A7, and A8, or 7A, or whatever. It depends on your periodic table. Sometimes it's listed straight across, but those are our group numbers. So this column has 1 valence electron. This column has 2 valence electrons. 3, 4, 5, 6, 7, and 8. Now, how does that help us figure out what ion forms? Well, it has to do with the noble gases, way over here, these guys. They are incredibly stable. They have a filled octet, and then that sounds kind of weird, but basically it means they have 8 valence electrons, okay? And that's what everyone wants. That's what all of these atoms want to get to, is a filled outer shell, that 8 electrons. And so if we go over here, we can see something like lithium has one electron, right? 1 valence electron. Now, to get to the noble gases, it would have to gain 1, 2, 3, 4, 5, 6, 7 valence electrons. And that's a ton of energy to do that, to shove 7 electrons in an atom. It's impossible. So what it does is it will lose an electron to be more like helium, to have the 2 electrons just like helium. Helium is our exception to the 8 rule because it's happy with 2. So the metals, which we just looked at, lose electrons. And when they lose electrons, remember, electrons are negatively charged, so when they lose electrons, they form positive ions. Nonmetals do the opposite. So nonmetals gain electrons, and they form anions, or negative ions. And you can use a number of tricks to figure it out by looking at the periodic table, but if you have their group number, you know their number of valence electrons, you can very easily see how many it needs to gain or lose. For example, over here, oxygen, it's got 6 valence electrons. To get to 8, it just needs to gain 2, right? if it wanted to go backwards, it'd have to lose 6. That's a ton of energy. So instead, it just gains 2 and becomes a negative 2. And that's the same for its whole group. Negative 2, or 2 minus, ionic charge. For the halogens, they all have 7 valence electrons. And so in order to get to 8, they have to gain 1. Gain 1 negative charge, they have a 1 minus, ionic charge. They have to gain 1 electron. For nitrogen's group, 5 valence electrons, has to gain 3, so we get a 3 minus. Boron's group, it's got 3 valence electrons. To get to 8, it'd have to gain 5. That's a lot of energy, so instead it loses 3. So we get a 3 plus. Over here, a 2 plus, and a 1 plus. This takes some practice to do. Notice I skipped group 4, right? It's got 4 valence electrons. It'd have to gain 4, lose 4. It's a bunch of energy either way. And so group 4, except with the exception of something like lead or tin, usually doesn't form ionic compounds. And it really just depends on what it's bonded with. So we're just looking at the other groups. And like I said, it takes some practice to work with. But once you get it down, the main group elements are super easy to figure out their charge. Again, they all want 8 valence electrons. Their valence electron number is equal to their group number. And so we can figure it out. Let's look at an example. Sodium has 1 valence electron, right? If we go back, it's in group 1, so it's got 1 valence electron. And so instead of gaining 7, it'll just lose that 1 extra electron. So here's that electron being kicked out to form a sodium with a positive charge. If we go back, we can see sodium. What I tell students is that if it jumps to the right, or if it's going to the right, so let's say nitrogen, it's going to the right, 1, 2, 3, that's gaining electrons. If it goes to the left, say magnesium, 1, and then over here to 2, to be like neon, that's going to be losing electrons, and so they're positive. It's kind of an easy way to figure things out. So sodium, it'd have to go all the way over here to argon, and that's a ton of energy. We don't want to do that, so instead it just jumps backwards to the left to be like neon. And so that's kind of one way to figure it out. A little trick. Again, something like bromine just needs to jump 1 to the right, gaining 1 electron. Let's look at chlorine. Chlorine has 7 valence electrons because it's a halogen. It's in group 7A. So group 7A, it's got 7A, not 8. 7A wants to get 8. It has 7 valence electrons. It wants to get to 8. And so it gains an electron. Here's that electron going in. And so we get a chloride ion. Notice the ending change from chlorine to chloride. Anions end in IDE. As long as they're monatomic, or just one element there, or one atom. And so this has 8 electrons, and it's got a negative charge. And so that's one way that you can figure out the charges for elements. And we'll use that to great effect in the next video when we're going to talk about ionic compounds.